Okay, you have been working on your graphing assignment number 2, which deals with graphing different parabolas and then analyzing how the parameters, that's the letters a, h, and k, how they affect the graph of y equals x squared. Today we're going to take a lot of what you've been discovering, put it into some notes, and make it more concrete so that you can refer back to it later, and so that we know how to talk about transformations using appropriate vocabulary and terminology. Before we do all that, we need to learn about this word. Zero. When we're talking about graphs, the word zero often comes up. We say, what are the zeros of this function? Okay, what are the zeros of this function? A zero is a value of x for which a relation has the value of 0. Well, that sounds confusing. It's not that confusing. If we have any old graph and we have a parabola on that graph, then we're looking for a value of x for which this relation, this light blue relation, has the value of 0. Well, if we're looking at values of the function, we're looking at the y coordinate of each point. So we notice that right here, the y coordinate is 0, because that's where it's crossing the x-axis. And right here, the y coordinate is 0. So these points are both called zeros. They correspond with the x-intercepts. Okay? So just to separate these two ideas in your head a little bit. Zeros and x-intercepts correspond very closely to each other. When we're looking at a graph, we call them x-intercepts. Okay? We call them x-intercepts. But when we say the x-intercept happens at x equals, let's say this is x equals 4, then we have the 0 of this relation. One of them is x equals 4. Maybe this is over here at negative 2. Then the zeros are x equals 4 and x equals negative 2. So the zeros are simply the values of x, so x equals 4 and x equals negative 2, for which a relation has the value of 0. So it's right where it crosses the x-axis, which makes them correspond with our x-intercepts. The rest of that page that you have in front of you is probably going to be taken up with notes on transformations. Transformation is any change to the parabola, is any change to the graph of y equals x squared. So for instance, if we make it y equals 2x squared, that's a change. Some transformation has happened. Or if we make it y equals x squared plus 3, some transformation has happened. Okay, there's two main types of transformations that we're going to talk about today. You're already pretty familiar with them. They happen with the parameters k, h, and a. So first we're going to talk about what happens with k, then we're going to talk about what happens with h, then we're going to talk about what happens with a. So transformations deals with the relation y equals a x minus h squared plus k. So we're going to find out what each of these letters does to the graph of y equals x squared. Starting with y equals x squared plus k. Does anyone remember what k does to the graph?
Moves it vertically.
Okay. K translates the graph of y equals x squared vertically k units. Now, If k is positive, which direction does the graph move? Up. If k is negative, it moves down. So we're going to make a quick note of that. If k is greater than 0, okay, that's a way of saying positive. If k is greater than 0, graph translates up. If k is less than 0, that's a way of saying it's negative. Graph translates down. Now off to the right, hopefully you have a little bit of space yet, but all we're going to do is draw a quick sketch of what we've said. Okay? So we're going to start with the graph of y equals x squared. Whenever you're talking about transformations of a parabola or of a quadratic relation, you're comparing them to y equals x squared. So in blue, we have y equals x squared. Then I'm going to add another parabola. It's going to have the exact same shape, but it's going to be translated k units up. So the pink graph here is y equals x squared plus k, where k is positive. And we're going to add an orange one here. The parabola's going to have the exact same shape. But the orange one is going to represent y equals x squared. And we're going to still say plus k, but we're going to show that it's where k is less than 0. Where k is less than 0. And to help us keep it organized, we should actually add that for the pink. That for the pink one, k is greater than 0. Ideally you'd fit that underneath your thing, but I don't have enough space in here. So k is greater than 0. So that's the effect of k on the graph y equals x squared. Okay? Let's tackle our next one. Am I good to erase here?
Yes.
Next we deal with y equals x minus h squared. Y equals x minus h squared translates the graph of y equals x squared horizontally h units. Occasionally, often, students will get mixed up with this one because the standard equation has a negative sign in the middle. Okay? So what that tells us is that, and you probably found out when you were drawing your graphs on Desmos, is that when you had a situation where it said x plus a number, like x plus 2, that actually moved it left 2, because that means that you subbed in for h negative 2. Negative minus a negative is a positive, right? So when this is a plus sign, it actually moves left, and when it's a negative sign, it moves right. Because if this is still a negative sign in here, then that means h was positive, which moves it to the right. Okay, so that note comes into play right here. If h is positive, if h is greater than 0, the graph moves right. If h is less than 0, if it's negative, the graph moves or is translated left. And again, we can draw a few examples there. Whenever we're drawing examples, we're going to compare it to the graph of x squared. So we'll draw that first. y equals x squared, I have in blue. Then where positive h is positive, that's going to move it to the right. So I want a graph that has the exact same shape. It hasn't moved vertically at all, but it has moved horizontally. So this orange graph is y equals x minus h squared. But we also need to note here that h is positive, h greater than 0. For my other parabola, some of my writing is going to get in the way, but that's okay. I have a parabola that's the exact same shape again. It hasn't moved vertically at all, it's only moved horizontally. And that shows me y equals x minus h squared, where h is less than 0. So again, if you were going to do an exact example, if you moved it over, let's say, 3 units down to -3, then this would look like y equals x plus 3 squared, because you would have minus a negative, which would be x plus 3.
Question.
So for example, if we know that this green parabola has been moved to the left 3 units, then we would say it has a horizontal translation, 3 units to the left, and if we sub in our value of -3 into our standard equation, we end up with x minus -3. X minus -3 becomes x plus 3 squared. So even though we have a plus sign in here, it moved to the left because the value of h is negative. Minus a negative is same as x plus that value. Okay, the last transformation that we have here is not a translation, but a stretch or compression. So when we look at what the parameter a does to the graph of x squared, okay, a is a stretch or compression of the graph of y equals x squared. There's one other thing that a does. A can also flip it, which we call a reflection. Okay, so first let's describe what a does. If a is greater than If a is less than 0, the parabola is reflected in the x-axis. So if a is a negative number, if it's less than 0, the parabola is reflected in the x-axis. So a bit of funny language there. It will make a bit more sense when we draw our picture, but that's what happens. There's 2 more bullets here. If a is greater than 1 or a is less than -1, so greater than 1 are numbers like 1, 2, 3, 4, 5 all the way up, right? And less than -1 means you're going -1, -2, -3. You're still kind of counting up, but in the negatives, right? So they're bigger values. What happens then? The graph is stretched vertically. The graph is stretched vertically. If a is in between -1 and 1, so if a is greater than -1 but less than 1, so that's what this interval means. A falls somewhere in between 1 and -1. That means it's a fraction, right? It's a fraction. The effect that has is that the graph is compressed vertically. So you're right that 0 falls in between -1 and 1, but a whole bunch of other numbers fall in between -1 and 1 as well. Okay, so if we think about our number line here, you can draw a number line, and you can think of a number line as having 0 here, and 1, and 2, and 3, and -1, and -2, and -3. Then this first bullet here, if a is greater than 1 or less than -1, includes all of these values, all the way down to negative infinity, and all the way up to positive infinity. Whereas this range between -1 and 1 only includes the values between -1 and 1. But if we zoom in on that little piece of number line, from -1 to 1, okay, there's a whole bunch of other values in here, like 1/2 and -1/2, or 1/4 and -1/4. Okay, so there's a ton of possibilities. These are fractions, but you could also show these as decimals. 0.1 is in here. 0.2 is in here, right? 0.5 is in here. -0.5 is in here. Lots of values fall in between -1 and 1, and all of those values result in a compression of the graph y equals x squared. Let's go ahead and draw a few examples. And it's going to get a little bit tight here, but we'll do our best. Firstly, we draw our basic example, y equals x squared. Okay, so in blue you have y equals x squared. And then the first note that we took said if a is negative, then there's a reflection in the x-axis. All that means is we have the same parabola, same shape, same size, but it's flipped upside down. So this red parabola that we've drawn is y equals negative x squared. All we did is add a negative sign in front, and it gets reflected in the x-axis. Well, let's see what a vertical stretch does to this thing. Makes it tall and skinny. So in our orange, we have a parabola that's tall and skinny. That is y equals ax squared, where x is greater than 1. Where x is greater than 1. Sorry, yep, where a is greater than 1. Good call. So that's ax squared, where a is greater than 1. Well, let's look at one that's stretched, but also flipped. This green guy, and I'll write his equation off to the side, off to the left here. This is y equals ax squared, where a is less than -1. So it's stretched and reflected over the x-axis. Okay, it's long and skinny and flipped upside down. That happens when you put a value like -5 in front of x squared. It gets skinny and it's flipped. I'm just going to draw one more. I'm going to draw a compression. A compression causes us to have a fatter parabola, a wider parabola. Okay, it's a vertical compression. So you can picture if you had like a ball or something, your parabola was a normal shape and you're squishing it down. It's a vertical compression which causes the parabola to get wider. So the pink there is an example where we have y equals ax squared, but a is in between 0 and 1. It's in between 0 and 1. I didn't include -1 in the range because that would, if it was a negative number, it would be flipped upside down. Okay? So you can picture what it would be like if a was in between -1 and 0, it would be just like this pink one, but flipped upside down. Okay? So right there you have a very good summary of all the transformations that we're going to be dealing with parabolas. Hopefully your notes are nice and neat, and you can refer back to them regularly. Some terminology that we picked up was horizontal translation, so many units to the left or so many units to the right. Vertical translation, so many units to the left, so many units to the right. Then we also have vertical stretch or vertical compression, and we have reflection over the x-axis. Okay, example 1, we are learning how to sketch a graph of y equals ax minus h squared plus k, given the equation. So we're given the parameters of this equation. So all we're doing is comparing the equation that we've been given with the standard parabola y equals x squared, finding out how it's changed, and that will help us to sketch our graph. Okay? So our parameters, when we compare with the standard form y equals ax minus h squared minus k, so compare with y equals ax minus h squared plus k. And we need to know what a is, we need to know what h is, and we need to know what k is. And that will tell us exactly how this graph is moving so that we can sketch it. Okay? So in this equation, in the equation that we're given, which is y equals 2x minus 4 squared minus 3. What is the value of a? What is the value of a? A is 2. What's the value of h?
4.
Excellent. Positive 4. What is the value of k? Negative 3. Okay, so let's describe what's happening here. We know, what does 2 do to it? What is 2 going to cause to happen?
Vertically.
It's going to be a vertical. Vertical what?
Parabola.
What does 2 do to the parabola?
Translated.
It doesn't translate it. That's what h and k do.
It just moves it vertically up.
Look back to your notes, please.
Stretch.
Stretch. Thank you. Vertical stretch by a factor of 2. Vertical stretch by a factor of 2. That's what A does. It's a stretch or a compression. That's it. A does not move the graph. It changes the shape of the graph. H equals 4. What is that going to make happen? Look back to your notes.
Either moves right or left.
So it is a horizontal translation of 4, which direction? Is h positive or negative?
Left. Negative.
H is
Positive.
positive, so it moves.
Right.
H is positive, so it moves to the right.
What? Well, we just pulled.
Okay? When there's a negative sign in the equation, it's moving to the right. Because h is positive. Because the standard equation is minus h. So in order for it to stay minus 4, 4 must be positive, which moves it to the right. Last one, k has a value of negative 3. What is that going to cause our graph to do?
Stretch outward and down. No.
Check your notes.
Up and down. It's not.
You can have stretch vertically.
Not a stretch.
Press
Up
vertically.
and down.
It's a vertical translation
Yeah.
of 3 units up or down? Down. Okay, so we have some of our basic information. There are other things that we can learn from this, though. We also note that A is positive. So is this graph opening up or down?
Up.
Opens up. Good. Good. If it were negative, we'd have a reflection in the x-axis. We don't. We also have how far it's moved horizontally and how far it's moved vertically, which means that we have the vertex. The vertex of y equals x squared is 0, 0. This graph has moved 4 units to the right, so the x-coordinate of our vertex is 4, and it's moved down 3, so the y-coordinate of our vertex is negative 3. Right? If we compare it to how it has changed from y equals x squared, which is a vertex of 0, 0, we've said it's gone 4 right, so the x-coordinate is 4, and it's gone 3 down, so the new y-coordinate is negative 3. Good. What is the equation of the axis of symmetry? If the vertex is at x equals 4, then the axis of symmetry must also be the line described by x equals 4. So what have we done so far? All we've done is describe the properties of our new parabola. Okay, we've described the properties. It opens up, it has a vertex here, has an axis of symmetry here. This is a description of the transformations. Okay? And now we have enough information to sketch it. Good? So on your graph, think about where you want your axes to be. You don't want to draw your axes right in the middle of your graph. Okay? Where is the vertex going to be? Yeah, it's going to be over to the right, and it's going to be down. So your vertex is going to be somewhere in quadrant 4. Right? So draw your grid so that you can show more of the parabola. You don't need a whole bunch off to the left, because most of the parabola happens off to the right, but you do want the x-axis to be kind of somewhere in the middle of the picture. Okay? So the balance of your graph should look something like this. Should be able to use 1 box per unit as you're drawing your scale, 1 box per unit. And now we can start to plug in the things that we found out. We found out that our vertex is at 4, negative 3. 4, negative 3. So we're going over 4, down 3, plugging in our vertex. We know it opens up, so it's safe to write our vertex directly underneath it. 4, negative 3. And we know that it's tall and skinny. Okay, we know that it's tall and skinny. We're gonna find out exactly how to draw like much more accurate ones, but for the sake of this example, all we need to know is that it's tall and skinny. So for instance, if this graph were gonna move over 1, x squared would move up 1, right? This one though is gonna grow twice as fast. So if you move over 1, it's going to move up 2. And if you moved over 2, x squared would move up 4. This might not make that much sense, but it will later. This one is going to go up twice as fast. So if we move over 2 blocks from the vertex, so over here to 6, we would have to move up, not just 4, but 2 times that. We'd have to move up 8 units. So anyways, this graph looks something like this. We're just drawing a curve, and it's skinnier than our standard curve, skinnier than our standard parabola. It doesn't have to be a perfectly accurate sketch, but there it is. Okay? We've noted our vertex, we also, just like every other graph that we ever build or sketch, we have to label the graph. This is y equals 2 x minus 4 squared minus 3. So that is B, sketch a graph. Okay? C and D talk about the domain and range. The domain is any value of x that can exist in the function. So for instance, if this parabola keeps going forever and ever and ever up, it's also going forever and ever and ever out and out. So this picture shows us that any value of x can be used in this equation. There's no number that exists that you're not allowed to put in here. You can put in 1, 2, 3, 4, 7.5, 5 billion. You can put in any value of x and the function will just continue to go and continue to grow. Same thing with negative values. You can put in anything you want. Okay? So x, this is for C, x can be any real number. I know you don't know the distinction between real and non-real numbers yet, but x can be any real number. D, that's the range. It talks about what set of values can y take. Well, if you look at your picture here, we're not talking about our x values. Now we're talking about our y values. We're talking about how far vertically can it go up or down. Do you think there's any restriction in the positive values of y? No, this parabola is just going to keep on going and going and going forever. But is there any restriction as we go into the negative values of y?
Yes.
Yeah. Because the lowest point on the whole parabola is right here at -3. So no y values can be less than -3, right? y has to be greater or equal to -3. So this statement includes all the values of y equal to -3 or greater, which is what our parabola can be. So this is domain and range. Example 1 had us sketching a graph given the equation. Example 2, you're given the graph and you need to come up with the equation. So again, we're identifying some properties of the parabola shown. The first thing, really easy to identify, where is the vertex?
1,
The vertex is 1, 5. Does that give us any other information that can help us derive an equation? Where do these values of the vertex come from?
point of where
Doesn't it show exactly how far horizontally and how far vertically the parabola has moved?
Yes.
Yeah, it's moved from 0, 0, right? The original vertex is 0, 0. So this tells us that we have h, because the vertex can also be represented, h, k, where h is the horizontal translation and k is the vertical translation. So now we know that h is 1. There's been a horizontal translation of 1 unit to the right. And k is 5. There's been a vertical translation of 5 units up. Tell me about A. What do you know about A? Remember, A talks about vertical stretch compression. It also talks about reflections over the x-axis. Has this parabola been reflected? Yeah, it's been flipped. Okay? So because the graph opens down, that tells us that A is negative. A is negative. Okay. Now we get to the step where we're going to start subbing in our values. We don't know what A is yet. Okay, we just know it's negative. So we're going to leave A alone, but we're going to sub our values for H and K into our original y equals ax minus h squared plus k. So we'll sub in 1 for h So we have x minus 1 inside the bracket, and 5 for k. So we have plus 5 outside the bracket. Okay? What else did the picture of the graph do to help us?
So this is the stretch.
One.
It gives us another point on the graph. Okay? Do you see that other point, 0, 2? It's telling you, what does it mean when a point is on a graph? That the values of x and y satisfy the equation. Yay! Okay, so we're going to use that information to solve for a. So we know that 0, 2 is on the graph. That means we know that if we sub 2 in for y and 0 for x, that this statement is still true. Well, now we have a whole statement of numbers and one letter. That means we can solve for that letter. Okay? This is where BEDMAS comes into play. First, we deal with brackets. Okay, let's deal with what's inside this bracket. What is 0 minus 1? Just negative 1. What's next in BEDMAS? Exponents. Exponents. Negative 1 squared is
1.
just 1, right? So 1a is just a. So all we have over here is 2 equals a plus 5. Now what do we do?
Oh, you can draw 5 from both sides.
We're going to subtract 5 from both sides. Subtract 5 from both sides. That tells us that a equals negative 3. Now we use this information, plug it back into our equation, because we want an equation that represents the graph that's given. So we already know that this is true, and now we know that this is true. So we can just use our parameters x and y again. And we get y equals, now we know a is negative 3, x minus 1 squared plus 5. This is the equation that matches the parabola. Okay? We can come up with equations in different forms, but this is the form we're working on today. It's called vertex form, but we'll learn that later. In example 3, we're dealing with a fireworks situation, and A asks us to determine an equation to model the flight path of the firework. So Vlad has read it for us. It's launched from a height of 2 meters, reaches a maximum height of 40 meters at a horizontal distance of 10 meters. So the first thing we're going to do to help us is to sketch a graph of the situation. Think about your x-axis and your y-axis. Okay, your x-axis is the horizontal distance in meters. Your y-axis is the vertical distance in meters. So how high are you going to do these numbers on your sketch? We don't need to worry about negative numbers. And we know that our maximum height happens at a horizontal distance of 10 meters. And because a parabola is symmetrical, okay, then I know the maximum we're going to go to is about 20 meters. The maximum height that we get to is 40 meters. So if I have a sketch and I'm splitting, trying to get my range here on my y-axis, both of them are distances measured in meters. And we know that we have a maximum height. And what's our vertex? Think about your vertex from the information given in the paragraph. What is your vertex?
2 meters from the ground.
0, 2.
Is that your vertex?
0, 2.
Or is that where it was launched from?
1040.
Okay, so your vertex is your highest point. Your highest point is up here at 1040. 40. Okay, an x value of 10, a horizontal distance of 10 meters, a vertical distance of 40 meters. Now, the point that you've given is the launch point. The launch point is 2 meters above the ground. So it hasn't traveled horizontally at all yet, and it's already 2 meters above the ground. So here you can note you have the point 0, 2. 0, 2. Well, parabola is symmetrical, so if it goes from 0, 2 to 1040, then it's also going to cross again right here at 22. And now we can sketch what our parabola would look like. Remember, as it goes to the top, it slows down, so it's going to be curved. And it's symmetrical. Doesn't have to be a perfect sketch. We're just getting an idea of what this thing looks like. And our goal in A is to determine an equation. So it's just like the last example. What do we need to do to determine an equation for this parabola? I'm going to give you the first hint, and then I'm going to let you do the next part on your own. We always start with the basic function, the basic equation, a x minus h squared plus k. So now we use the information that we know. What do we know that we can plug in? Yeah, you know the vertex. And the vertex is hk. So go ahead and sub in the values that you know. Check the board to see how you're doing.
K 40.
K is 40.
They've also given us another point on the graph. How is that point going to be helpful? Yeah, we want to find out what A is. We don't know what A is, but we do know that we have a point, xy, that satisfies the equation. So go ahead and sub those values in. You should be left with an equation that just has one variable left and a whole bunch of numbers, which means we can solve for A using BEDMAS, our order of operations. You go ahead and try that first step. You're taking care of the brackets first. In the next step, we're taking care of the exponent. In the next step, we need to try to isolate A. Right now, it's attached to 100 by multiplication, but we can subtract 40 from both sides. Now A is still attached to 100 by multiplication, so we'll have to divide it by 100. Which means we have to divide the other side by 100. A equals negative 38 divided by 100. That is just a decimal. Negative 0.38. Well, now that we have a value for A, what can we do with that value?
Plug it into the original equation.
Plug it into the original equation. So we've got y equals, here's an equation that already has some important information in it. So we're putting A into that one. Y equals negative 0.38 times x minus 10 squared plus 40. That's the equation that matches the flight of the firework. It tells us exactly where the maximum height is, 40 meters, tells us exactly at what horizontal distance that happens, 10 meters, and it tells us the shape of the parabola. It is a vertical compression by a factor of 0.38, and it is reflected over the x-axis. Good. A is done. Let's look at B. What does B ask us? B says, the firework continues to travel an additional 1 meter horizontally after it reaches its maximum height before it explodes. So it's traveling, it's going up, and after it reaches its maximum height, it's going to travel another meter horizontally. So from here to the place we're considering is 1 meter. It's going to travel another meter before it explodes. So right at this red point, it's exploding. Okay? What is the height of the firework when it explodes? What is the height when it explodes?
35, 12.
So you can look at your picture and you can kind of estimate where it explodes, and that'll get you pretty close. Or you can use the equation that you just built. And you can sub in a value that you know. Well, where it explodes, we actually know the x-coordinate of that point because we're told that it's going to travel 1 more meter horizontally. So what's the x-coordinate of that point? 11. Okay, so let's sub in what we know. We know that x is 11. Now we have an equation where all we are missing is the value for y, which is what we need, right? Because y is the vertical height of the firework when it explodes. So here we go. Inside the brackets, 11 minus 10 is 1. 1 squared, 1. 0.38, negative 0.38 times 1. Yeah, it doesn't change. Negative 0.38 plus 40. And you could use your calculator. Hopefully you don't need your calculator. You're doing 40 minus 0.38. So you've got 40 minus 0.38, so you're going to be 39 point something, right? 39.62. The firework explodes at a height of 39.62 meters. 39.62 meters. Now, the next question, question C, has everything to do with the symmetrical property of parabolas. So read question C. It says, at what other horizontal distance is the firework at the same height as it was in part B? So at part B, the height was 39.62, and it happened at 11 meters horizontally. Where else on this parabola, this whole green parabola, where else is the firework going to be at the exact same height as it was here?
Nowhere.
Yes, over
On
on
the
the left side of
ground.
the parabola.
Oh, so just as far to the right that we went for it to explode, we have to go just that far to the left,
Yeah.
and we'll get the exact same value. So how far did we move from the vertex to the right?
One.
We moved 1 meter to the right. So how far do we have to move to the left? 1 meter to the left. Okay? So the answer for C, the answer to C, you're going to write this. Due to the symmetrical nature of parabolas, or a parabola, the firework is at the same height 1 meter before the max point. So if it exploded 1 meter after the max point, then it will be at the exact same height 1 meter before the max height, which is, just go period, and then just say x equals 9. Okay? X equals 9, that means a horizontal distance of 9 meters. 9 meters from the launch point.
Pop it up pretty quickly.